Okay, let's see if this works. Hello Internet, my name is Quinn and this is Blondihacks. I'm going to make a tool today that you don't see very often, but it's actually really cool. Especially here in the hobby shop, it is just the thing for a lot of tricky setups. It's called a cat's head, and I'm going to show you how to make it right now. Let's say you need to put a feature on the end of a really long piece of stock like this. Maybe it's too big to go through the spindle bore, or maybe there's features further down the stock that will prevent you from gripping it close to the chuck, so you need to work on it way out on the end. So normally you'd set up a steady rest, right? No problem. But what if your stock is square, or hexagonal, or another odd shape? Well, let's go ahead and set up the steady rest anyway and see what happens. Okay, I'll just go ahead and power up the machine now. I'm just kidding. Okay, let's be honest. How many of you pooped your drawers just now? Of course, that would be catastrophic to something if we tried to do that. Now, the solution to that is called a cat's head. It's a very simple tool, and it's surprisingly cool. So it's just a cylinder made out of something like steel, and it's got set screws in different patterns around the outside that will allow it to grip onto square, hexagonal, round, or other even odd-shaped stock. And what it does is it gives the steady rest a consistent round machined surface to ride on. It effectively abstracts away the surface of your part into a simpler form that the steady rest can understand. That's sort of a software engineering metaphor, but you get the idea. First, we need to figure out what the largest diameter thing is that will fit in our steady rest. And this turns out to be kind of hard to measure, honestly, but I found it was just easiest to find a bunch of round things in the shop and try them. This bottle of Dicam seemed to be about the best fit. You want something that's kind of at the limit of your steady rest, but still gives you a little bit of adjustment on the legs. To figure out how long that tube needs to be, I'm kind of mocking it up here with my steady rest. You kind of want room for a dial indicator on either side, and you need to be able to access the set screws with it in the steady rest. And I landed on 2 inches as a good length. Now to make it, I'm going to dig through the junk pile, and I've got some mystery steel here. You know, in my early days of machining, I wasn't very good at labeling my stock. I didn't have very much of it at the beginning, and I always forget that I shouldn't rely on my memory. I thought I could just remember what everything was, and obviously that was naive and foolish. So I don't know what this stuff is. It's some kind of mild steel. I know that it's not 12L14, so it may be difficult to machine, but we'll see. Well, whatever it is, the trusty horizontal bandsaw will lop a chunk off of it for us. I'm going to set this up in the 3-jaw here, and we have a fair amount of stick out, so it's not unlikely that the part is a little crooked in those jaws. So I'm going to just throw the indicator on the end here, and yeah, sure enough, we've got some run out. There might be a little bend in this as well, but I can just tap that guy in a little bit, and this will help straighten it and or average out whatever bend might be there. So we got it within 10 thou, which is frankly probably within the surface rust there. I'm going to start by facing the end, as is tradition. And this is my standard go-to tool bit for steel. Seems to be cutting okay. There's a lot of rust on there. You can see the rust accumulating on the tool bit. What a mess. Sure does look nice cleaned up though. Feels okay. Now we'll throw a number 2 center drill in there, and we'll punch a center in the end for some tail support. And speak of the devil and he shall rise. There is our tail support. Square up my tool post here to get ready for turning. Mark myself a generous amount of length here and make sure I can get my whole part in there and room for parting. And lots of cutting fluid, and let's see how it goes. So I'm starting with a light skim cut of 20 thou just to get the rust off of there, and you can see what a mess it's making of the tool bit there. That went okay, but my first real cut did not go well. It is chattering first of all and not making a chip at all. Clearly we need more rigidity here. I noticed that my compound was unlocked, so I locked that down, and I also enlarged the center to a number 3 for better support there. So the chatter is now gone, but it's still not cutting very well. The chips won't curl and thus won't break, and you can see what's happening. It's making rat's nests almost like aluminum does, and then the chips are getting overheated because they aren't breaking and carrying away the heat, so they're turning yellow and purple, and it's really a mess. I tried all manner of speed and feed combinations, nothing was working. So I tried a different tool bit. This is an older one that I ground that has a really large nose radius on it, mostly because I didn't know what I was doing, but it actually cuts quite well, and this is actually curling a much better chip, and the chips are even breaking pretty decently, but I can't cut very deep with this. I can only get about 10 thou. Wait, is that carbide in the Blondihacks shop? Why, yes it is. I don't use it a lot, but occasionally it's just the thing. Something like this where I've got mystery steel that won't cooperate, sometimes carbide gets it done. The sophisticated chip breaker geometry and its ability to absorb massive amounts of heat is really getting the job done here. You can see those chips are still coming off yellow and blue, but they're breaking, they're taking the heat with them, and we're getting a decent finish. I'm still a little bit limited on depth of cut. I'm not able to go any deeper than about 20 thou before it stops curling that chip again, but this is getting the job done, and we don't have that far to go, so this will work. But toe peak of that part was hot. That was toasty when it came off of there. Keep an eye on your tailstock when the part's cutting hot like this, because it'll expand and overwhelm the clamp on your tailstock and push it outwards. And then if it cools off and contracts again, now your tailstock isn't properly seated and you'll lose rigidity. Okay, I'm on the dimension of the Dicam bottle, so now I'll get the steady rest in here and see if it actually fits. And well, it doesn't. You can see that one of the rollers there doesn't quite clear, but the other two have plenty of clearance. So what this means is the opening in the steady rest is pretty poorly centered on the axis of the lathe. It's a budget hobby machine tool. You get what you pay for. So I needed to reduce the diameter a bit more in order to make room for that one roller there that's tighter than the others. And now I'm just double checking my length to make sure I'm going to have room for all of the hardware. And the steady rest is going to be valuable here on the next step, so we might as well just leave it here and make it official. We're going to be doing some heavy drilling and then some boring to get that center diameter where we need it to be. And while I'm here, I'll chamfer that edge real quick. This is jumping the gun a little bit, but I really love chamfering. I'm going to start with the drills, and we don't need any precision on this depth, so a Sharpie and a ruler is fine. I just got to make sure I go deep enough to get past the parting line that we're going to need. So I'm starting with this pilot drill. I think it's 3/8 maybe? I don't know, it's smallish. You can see that this mystery steel is not even drilling well. I don't know what this stuff is, but it's pretty terrible. You can see it's making really weird, inconsistent chips, and there's also hard spots in it, which I noticed when I was turning as well. It would be turning okay for a while, and then there'd be like a clunk as it would hit something hard in the steel. You can see that in the drill chips as well. It'll make okay chips for a while, and then the chips will get all spaghetti for a while. And the larger drills made really crazy spaghetti chips. And for the largest size, I've got this really nice reduced shank bit. This was a recent donation to the channel. It's got a little rust on it, but we're about to remove that, no problem. And this was just the thing for this job. So thank you very much for all the viewers who donate tools to the channel. It really is a big help. But look at the rat's nests I'm getting. These drills even are not cutting well. I'm determined to defeat this garbage steel though. No matter how much cutting fluid I use, every operation is crazy hot with this steel. So those drills are coming off of there too hot to handle. And the last thing is to bore it out to the final dimension. I'm using this boring bar that I bought a while ago and never really ended up using because it was too large for most of what I do, but it's just the thing here. It's got some mystery carbide insert in it that's doing pretty well. For diameter on the interior, I basically want it as large as I can get it because that'll give us the most options for holding stock inside the cat's head, but you want to leave plenty of meat for the set screws to thread into. And predictably enough, the finish in there is pretty terrible, but it won't matter very much. So then I'll chamfer that inside edge to match the outside. We're done with the steady rest for the moment, so we'll get this out of here. And I'm going to see if I can improve the finish on the outside of that part a little bit. It's okay, but you know, we can do a little better. So I got some 320 grit emery paper. I got the surgical dressing down on the lathe. And we'll spend some quality time with the emery paper. I moved up to 600, and then I think I spent some quality time with 1200 or 2000, I don't know, something higher. And you can, you know, spend all day on this. The thing about emery paper is that it's diminishing returns. It takes longer and longer to get slightly better and slightly better results. So it's as good as your patience. To try and improve the inside a little bit, I did something slightly ill-advised. I wrapped some emery paper around a piece of electrical conduit and did my best to polish the inside. I'm holding it with pliers because I don't like to hold something that might potentially grab and spin with my hand. I think that's just dangerous. It's a little better, still not great. Okay, calm down. I hear you giggling out there. Stop it. And then I'm just going to mark about 2 inches of length. Precision is super not important here. This is just a ballpark woodworker grade operation. And because this mystery steel has been so ornery, I'm going to retract my parting blade in as tight as I can get it here and maximize my chances of success. I have a feeling it's not going to part well, but of course that means I got to adjust the center height because of the angle of the parting blade holder. And then I'll square that up on the end of the work and cross our fingers, sacrifice a goat to Metallicor, the god of machining, and it's going okay. It's wanting to chatter. So I had to slow it way down, even slower than I would normally go for steel of this diameter. So I'm down to about 50 RPM here. Don't normally go below 100 RPM on this lathe. It's definitely struggling a bit, but it is getting it done. Now, if you're used to larger lathes that control their RPM via gears, then you might be confused by this. On larger lathes, of course, they gain torque at lower RPM because of gearing. On these brushless DC hobby lathes, they lose torque at really low RPM because they're not using gears to change the RPM. They're relying on the switching speed of MOSFETs, and they lose a lot of efficiency at these really low frequencies. And Yahtzee. Now I'm going to flip the part to do a couple of cleanup operations. I'm using soda can there to protect the part. I have soft jaws for this 3-jaw chuck, but they introduce a fair amount of runout, so I don't want that in this case. And we can remove that extra little can opener edge there with some pliers, and then come in and chamfer the edges. You can see there's some runout there. Probably about 5 thou is what I get when I reverse a part in this chuck. So technically those chamfers aren't concentric, but no one's ever going to see this. I think this whole internet thing is a fad. With the lathe work done on our part, I'm now going to chuck up some aluminum scrap. And why am I doing that? I'm going to make a mandrel to hold our tube here for the next set of operations. They're light duty operations, so aluminum is going to be fine, and it's going to be very fast to do our machining with this. So all I got to do is turn down the outer diameter to 1 inch exactly, so I can hold it in a collet. Now this stock is already basically 1 inch nominal, so I couldn't quite take enough off to clean up the diameter, but that's okay. And I'll put a little witness mark there based on the length of my part. I need the mandrel to be a little shorter than the part, and we'll just buzz that material right off of there such that it'll fit inside our tube. And a little chamfer on there so make sure it slides on nice. Then I'm going to drill and tap the end for a screw, giving myself lots of extra depth there so that I can just use a taper tap and get deep enough for the screw. So there's our tapping size, and then I'm going to come in and tap those threads. I don't even remember what size this is because it really doesn't matter. And we'll do a little test fit here before I take the mandrel off the lathe. So that tube slides on there. You can see that the mandrel is a little bit shorter so that when I clamp this washer on the end, it's going to clamp our part to the mandrel. Looking good, nice and concentric. Now I can part this guy off. And actually, no, I can't because the blade is still set really short from before, so it wasn't long enough for this part. So rawr, Quinn smash. I had to just break it off at the end. It'll be inside the collet. No one will ever know. Lastly, I just need to make these threaded holes. And the pattern looks odd, but what it is a 4-hole radial pattern with a 3-hole radial pattern overlaid such that the two patterns share one of the holes, just to minimize the number of holes. Like anything in machining, there's 1,000 different ways you could do it. Let's look at a couple of options for ways to do this. So one way would be the rotary table. So if your rotary table has a machined bottom, you can set it up vertically and just fixture that guy on the plate right there and rotate it at will to get all of your holes drilled. And I almost did that because rotary tables are fun and cool. Another way to do it that's a little lower precision would just be with layout. You could mark the radial pattern on the end of the part and then transfer it to the length with a protractor or with the surface plate and a height gauge. But I decided to do this with collet blocks, so a square block will give me the 4-hole radial pattern and the hex block will give me the 3-hole pattern. We need to find the center axis of the part, so edge finding is a great way to do that. However, sometimes on a large radius part, the edge finder can't reach all the way down to the equator, if you will, of the cylinder. So here's another way to do that. Now, if you have a depth stop on your quill, one way to do it is to simply get down to the same depth on either side of the part, and then you're measuring the same circle chord on either side, so that's a valid way to find the center line. But here's an easier way for this particular setup, which is just to use the edges of the collet block. We could also use the vice jaws. Now I'm going to mark out where to put my hardware. Just, a reasonable distance in from the end is all we care about. And I'm just lining that up by eye and setting zeros on the DRO so that we can repeat this location for all the other holes. Now when you need to drill onto the top of a convex surface, a center drill can be used to very carefully peck at it and make a dent so that the drill won't wander off the top surface. And I'm going to use the collet block to repeat that operation on all of our holes. Another way to do this is to make a little flat spot with an end mill, and that works especially well if you're drilling off-center on a convex surface. And now to the drilling. So this is the 4-hole radial pattern that I'm starting with, so these can just be drilled all the way through. The other advantage of that aluminum mandrel is that it's very easy to drill through. And drilling through means we only have to do this twice to get each of the 4-hole patterns. So this is a very quick operation. Now to overlay the 3-hole radial pattern, I thought I was being pretty clever. I just transferred the entire collet part assembly over to the hexagonal block, and the keys on the collet blocks will keep the timing consistent between the two setups. And then I can just pick one of my holes to be the shared hole and then rotate the block 2 steps between each of those to get the 180-degree angles for the other holes. That works in principle, however, I screwed it up a little bit. If you're going to do this, you got to make sure to choose a shared hole that is on one of the points of the hexagon and not one of the flat sides, because that means the flat sides are in the vise. And across the flats, the hexagon is the same size as the square in a collet block set like this. That's pretty simple, and yet I somehow managed to mess that up, and my first hole wound up in the wrong place. So I had to start over with my 3-hole pattern and use the points in order to get out of the way of my error hole. So I ended up with a, let's call it a speed hole on that one side, but I had to also redo the center finding for the hexagonal block because it is wider in this orientation. So I used the 0 on my incremental scale on my DRO so I could keep track of the 2 zeros for the 2 blocks. To drill the holes on the far end of the part, I did something that I thought was pretty clever, but actually isn't, which is simply to flip the part end for end. That eliminates the need to have support at the end of the part when I'm drilling out there, and it solves the problem of not being able to drill through where the bolt is in the center of the mandrel. So I flipped the part end for end, and then I used a drill bit to get the timing back where I had it on the what I've designated my number 1 hole. It actually would have been simpler and more precise to just drill the holes on the far end with a machinist jack under the mandrel and just don't drill them all the way through for the 4-hole pattern. But this did work, so rinse and repeat on the other side. Now it's time to tap the holes, so I got my spring-loaded tap follower in there, and I just went through the same procedure that we did for drilling, and I tapped them all. And I'm using 832 hardware here, and I'm just verifying that the depth is sufficient. It's hard to tell how deep I am because I'm drilling into a mandrel. And just like with the drilling, the collet blocks give me my repeatability, so it's very easy to index through my holes. Now after all that, the mandrel was pretty thoroughly stuck in there from all of the burrs and threading and so on, so I had to tap it out of there. And then all that was left was to deburr the holes. I'm using a Noga tool for that. Now the outsides are easy, but look at that mess on the inside. How are we going to deburr that? I'm going to do that with this guy, which I think is one of the sexiest tools in my shop. It's from Noga. It's a collapsible inside deburring tool. So the blade on it folds up, allows you to stuff it through a hole, and then expand the blade on the far side with a button push, and then you can pull it back and deburr the back side of your holes, just like that. And then when you're done, the blade collapses and you can pull it out again. I've shown this before on my channel, but I love it so much that I just had to show it again. Hashtag not sponsored, but if you want to buy this guy, there is a link down in the description. Ugh, it's so cool. And now it looks like tiny little gnomes went in there with tiny little needle files and fixed all of my burrs. Okay, a little bit of hardware and we're ready for a test run. So this is the 3-hole pattern used for round stock and hexagonal stock. And then this is the 4-hole pattern, which again shares one of the holes. And this is for square stock or anything odd shaped is probably going to be usable with the 4-hole pattern. So I'm going to test it out with this brass square bar here. So we'll dial this guy in on the 4-jaw. This bar has kind of a bend in it, so I'm tapping it in as best I can, but I can't get all of the bend out of it, but that's actually going to be a really valuable demonstration of what the cat's head is capable of. So you can see there's a fair bit of run out there. There's maybe 10-20 thou run out at that end, but fear not, we can set up the cat's head and I'll show you some magic. So here we'll center drill the end, and then we bring in the steady rest, and then you want to put the cat's head over it now and not slide the tailstock in like I did in this clip. So pretend I had remembered to do that. Then you tighten the set screws down over the material, and you can protect the material with aluminum shims or something if you need to. And just sort of center it by eye as best you can on all 4 sides. And then you bring in a dial test indicator and you dial it in like you would a 4-jaw chuck. Now the set screws are pushing the cat's head away from the material, so the movements that you do are opposite what you would do with a 4-jaw, so that takes a little getting used to. We've got it within a thou there in the center, but now we move it down to the end. You can see we've got about 5 thou of run out there. So we're going to dial in that end using only the set screws at that end. And then we do the same thing at the other end. And once the 2 ends and the center are all running 0, then the cat's head is genuinely running true. And what that has done is canceled out any angle or imperfections in the length of the material under that cat's head. So now we can bring in the steady rest and set it up just like you would on machined round stock. And now we can pull the center out, and there's the magic. So you can see the run out in that brass bar. You can see the bend and how much it's running out, but the cat's head is running perfectly true. So what's happening is the set screws are at slightly different lengths inside that cat's head, and they're canceling out the angle that's in that stock because of the bend. And so the cat's head itself is running true, and so the steady rest is none the wiser that we're running this crazy stock inside of it. So we can come in here and face off the end, no problem. Facing is easy though. What if we wanted to put a feature on the end of that part? So let's turn a little round boss on the end of this crazy square stock. Now of course this is an interrupted cut, but you can see that the cat's head is absorbing those cutting forces, no problem. And there's our beautiful little boss feature, perfectly concentric with the axis of the lathe. And you can see how the stock is way off of that axis. Tons of run out there, but it doesn't matter. The cat's head has canceled all that out for us and allowed us to create a perfect feature on the end of this bent square stock, way far away from the chuck. No problem. But wait, the cat's head has one more amazing trick up its sleeve. This is a common problem. You're working on long, thin stock through your spindle bore, and this stock is going to tend to flop around when the machine is running. And that can cause the stock to bend. It could even damage the spindle bore and cause other mayhem. So take our friend the cat's head, and if you take out one row of the set screws, now you can just slide that on there, and if you size it appropriately so that it's a precision fit inside your spindle bore, that'll just slide right in there, and then you tighten these guys down, and you can put an indicator back here and get it centered up just like you would with a 4-jaw, and it'll run true all the way through the spindle. You don't need anything holding it into the spindle bore because it's clamped to the material, and the material's clamped in the chuck, so it's going to stay here, and it'll spin with the spindle and just keep this material centered in the bore and keep it from flopping around. Sometimes when it's used in this configuration, people call it a spider. Yeah, you can call it a cat's head, call it a spider, whatever you like. So that's what a cat's head does. You can see how easy it is to make one. It's a really cool tool, especially in the hobby shop where we're working with a lot of long, skinny, odd-shaped stock. I hope you'll make one of these guys. It's a very fun little afternoon project, and I hope you enjoyed this video watching me make one. Thank you very much for watching. Consider throwing me some bucks on Patreon if you wouldn't mind, and I'll see you next time.